Good afternoon. Good afternoon, everyone. So, yes, I will speak about magnetotransport since that's experiments I'm mostly doing in topological materials. So, in our group, we are mainly doing 4-6 semiconductors, and recently we started to work with tin as a semi-metal. So this is the approximate plan of the talk. So first I will introduce the material we are mostly working, these topological crystalline insulators, which are based on 4-6 semiconductors. And then I will discuss published results on lead-tin selenide films regarding weak anti-localization and how the symmetry affects the Berry phase quantization in such system. And also I will mention our recent results on spin result ARPES, which are somewhat aligned with this weak anti-localization experiments. And then if the time allow, I will talk about unpublished results on two directions which we are working right now. One is lead-tin selenide quantum wells. So I will show results, some magnetotransport on Shubnikov-Degas oscillations, and discuss whether we can achieve at least quantum Hall effect there. And then I will talk about alpha tin, which is some crystal modification of tin, which is a semi-metal, and I will show our recent results on magnetotransport and Shubnikov-Degas oscillation analysis. So what we are working, the main interest of our work is some topological properties of solids. So the most known example is topological insulators, which are already not that much novel material after all these years. So what are they? So in simple words, they are insulators in the bulk, but have some conducting edge states in 2D case or surface states in three-dimensional case. So they are characterized by topological Z2 index, which is number of crossings between Fermi level when it's laying in the bulk gap and edge states. And the most important is that they are protected by time reversal symmetry. So this surface states has so-called spin momentum locking. So the direction of carrier moving is locked with the spin orientation. And also it was shown that these surface states or edge states has a linear dispersion, and this Dirac cones, how it's called, such linear dispersion, have helical spin polarization due to this spin momentum locking. However, quite soon it was realized, but that time reversal symmetry is not the only possible protection for such systems. And also crystal symmetries can be responsible for the topological protection. And materials where the crystal mirror symmetry was responsible for topological protection was called topological crystalline insulators. So these are cubic crystals where the topological phase is protected by the mirror symmetry of 110 planes. So now they are characterized by different topological number, is mirror chair number. And it was shown that tin telluride is simple example of such a system, and it was already known that it can go to the trivial phase with the usual band ordering in lead telluride, simply by allowing this to compounds, and at certain composition the band inversion occurs. The similar things happens in selenite, in lead selenite, where one also can achieve band inversion by changing the composition. And what is also important here is that the Brillouin zone is the Fermi surface in the Brillouin zone is projected differently on 100 plane and 111 plane. So it has pockets in L points, and they're projected in different places on these two surfaces. So they have slightly different properties. What I will mainly talk about are 111 surfaces. So if I do not emphasize, just keep in mind that I'm talking about 111 surface where it has Dirac cones in gamma bar and M bar points. So since I'm doing magnetotransport, so I will go a little bit in the different direction and discuss the weak localization phenomena, which is simple interference phenomena. So let's consider the simple problem of passing the carrier from the left to the right. So there are two contacts. And the simple way is just to calculate the amplitudes of all possible paths and to add them. So they will also contain such term, which is interference term of different time reversal paths. And the special class of paths are such paths with the small self-intersecting loops, which can be where the carrier can go in two different directions. So if the size of the loop is relatively small, that the phase of the carrier is conserved during going on this loop, then the electron waves of two different directions will interfere with itself constructively, and it means that the carrier tend to stay on such small loops. So it will not go, it tends not to go further, but to stay on place. And if one calculated, he can get that such effect is manifest itself as some negative contribution to the conductivity, which is has some logarithmic dependence on the size of the loop relative to the inelastic scattering length, over which inelastic scattering length is the length over which the phase of the carrier is conserved. And the order of this effect is E square over H, quantum conductance. So it is a pretty small value. So to observe the effect, one should look into a little bit more resistive samples like semiconductors. However, in metals you also can observe this, but it's much harder. So, but usually such effect is studied as a function of magnetic field. So what does magnetic field? Magnetic field adds an additional phase difference to these two paths. And due to the fact that these loops can have different shapes, it is averaged out to 0 in the end. So, and calculations show that in two-dimensional case, such correction to the conductivity has logarithmic dependence on 1 over b. And quite an unusual effect on this weak localization is done by spin-orbit interaction, which first is reducing the amplitude of the effect by a factor of 2, and also change a sign of the effect. So the system in the presence of spin orbit and zero magnetic field becomes more conductive rather than less conductive. And that's why it's called weak antilocalization. That's how these both effects manifest in experiment. So here you can see in magnesium films that around zero field it has increase of resistance, so it is less conductive, and addition of gold on the surface result in the increased conductivity or reduced resistivity. So detailed calculations of the effect result in such quite bulky formula, which contains information about the different scattering events. It is from the seminal work by Hikami, Lark, and Nagaoka. That's why it's called HLN formula. But in the presence of strong spin orbit, this bulky expression is reduced quite considerably. It depends only on the inelastic scattering length, and prefactor alpha is responsible for this indication for number of conducting channels in the system. Quite soon it was realized that spin orbit is not the only effect which can lead to these weak antilocalizations. So there are different mechanisms which are leading to the same effect. Of course, it is interfacial Rashba field or Elliott-Yaffe mechanism of spin relaxation, but also it was found that in Dirac systems with linear dispersion, where the carriers can obtain additional pi Berry phase, the backscattering is also reduced, and this effect mimics the weak antilocalization effect and manifests itself the same way, though spin orbit interaction, for example, in graphene is quite small. Also, this effect is expected for topological insulated surface states with the spin momentum locking. So such effect was used quite often as a poor man test for directness of the material. So one can find such boards that weak antilocalization can be indicator of topological materials. So within our work, we considered how these different symmetries affect weak localization effects through calculating the Berry phase and how it is changing due to constraints imposed by different symmetries. So for time reversal symmetries, it has the following constraints on the Berry phase, and it was found that it leads to the quite trivial consequence that for strong spin orbit we have pi Berry phase, which means that we should observe weak antilocalization, and zero Berry phase for absence of spin orbit, so weak localization. So that was quite trivial, but also we considered the effect of mirror symmetry, which also impose different constraints. And we found that mirror symmetry also can be responsible for the quantization of the Berry phase. So application of these considerations to the real material, like tin telluride, or just any material with a similar cubic crystal for 111 surface. So we calculated Berry phase for different Fermi pockets around gamma points, gamma bar points, and three equivalent M bar points. So in the case of when mirror and time reversal symmetry are both obeyed, then we see that Berry phase is quantized to pi. However, if we break time reversal symmetry, not everywhere Berry phase is quantized. Somewhere it's randomized, by mirror symmetry is still responsible for the quantization of Berry phase for high symmetry points laying on the mirror plane. So to zero the barrier phase, one need to violate both time reversal and mirror symmetries. So calculations of the conductivity based on such symmetry analysis result in the correction to the conductivity, which looks quite similar for the HLN expression for strong spin orbit limit. However, now the phase coherence length or inelastic scattering length is replaced by the effective value, which depends on, of course, usual inelastic scattering length, but also on the some length scale associated with the symmetry breaking. So this limit the growth, the rise of the inelastic scattering length with the temperature. So it is not growing, but saturates at a certain value. And that results in the suppression of this weak anti-localization effect for the case when mirror symmetry is broken. Opposite to the case when mirror symmetry is obeyed, where the effect at low temperatures is much stronger. So we got from theoretical considerations that we should observe weak anti-localization in both topological and non-topological cases, because in this consideration we did not consider the band inversion, only symmetries. So the symmetries, rather than topology of the system, is determining the weak localization behavior or barrier phase quantization. And also we can see that present symmetries, for example, mirror symmetry, is crucial here. So to test this, the two different groups of the samples, which can be divided in two different subgroups, we have grown total 10 samples. So it is leptin selenites, thin films about 50 nanometers on barium fluoride substrate. So two subgroups were, one is trivial and inverted samples with different selenium, with different tin composition. So here one can see how the band inversion occurs with the changing of the composition. So in our case, tin ranged from 0 to 0.3, covering both trivial and topological cases. And another subgroup was bare epilayers without any cover, and epilayers covered with amorphous selenium. So amorphous selenium was used as a symmetry breaking layer because it is amorphous and it doesn't contain any symmetry. The quality of the films was checked by IFM, which showed very low roughness and pretty nice XRD, which showed high crystalline quality of the samples. These epilayers were also checked with ARPES to show that we indeed cover both cases, topological and non-topological. For that, we used films with amorphous selenium, which was evaporated in the preparation chamber, and we saw that indeed in films with low tin composition, we have a gap opened in all temperature range. However, in the samples with high tin composition, we see that the gap is closed, the surface gap is closed at low temperatures. What is important here, we also did not see any signatures of the Rajka splitting. So to measure magnetotransport, we etched such as rather small hole bars on the in the films. So we used the electron beam lithography to put this whole bars on the flat areas on the cleaved barium fluoride steps. So here the black lines are etched trenches, and such bluish color is lead-zinc selenide films. So this is the list of all studied films. Blue corresponds to topologically trivial cases, and green for topologically non-trivial cases. So magnetotransport was quite typical for disordered conductor with high field magnetic resistance changing from parabolic to linear dependence, which is described by such semi-empirical formula. And the whole effect showed quite high p-type concentration. What is important here that weak antilocalization effect we saw in all studied films. So it's kind of first check that the symmetry considerations I presented above were correct. So now let's see how weak antilocalization in these films behaves as a function of temperature. So in bare epi layers, we measured at different temperatures magnetic conductivity and fitted with Hikami-Larkin-Nagaoka expression for strong spin orbit limit. We extracted L-phi in elastic scattering length, and we see that it is growth linearly in the log-log scale as it should be. And prefactor alpha was 1/2 as it should be. So everything is fine. However, in the selenium covered films, we see that the inelastic scattering length saturates as we cool down the system in all films. So if you compare these results for all the films, it really resembles the picture I showed above from theory, that when mirror symmetry is obeyed, inelastic scattering length is growing without any tend to saturation, opposite to the case where the M symmetry is broken and it limits the growth of L-phi. So also the temperature dependence of L-phi was consistent with electron phonon dephasing process, which is expected for such material, since it is known that at low temperature the dielectric constant here is pretty high and electron-electron interactions are suppressed. So, however, in principle, such saturation of L-phi is not something very unusual. One can get it due to different reasons. And the most common are heating effects, finite size effects, or some other length scales which are limiting the rise of L-phi. In our case, we do not believe that any of this can be the reason for the observed saturation, since we used pretty low currents down to 1 nanoampere, and we saw that weak antilocalization is suppressed in selenium covered films still at 1 nanoampere. The whole bars we used were pretty large compared to the observed values of L-phi. So it was something like 10 to the from 10 to 100 microns. Spin orbit length we also estimated with the fitting with the full Hikami-Larkin-Nagaoka expression, and we confirmed that spin orbit length scale was always smaller than the value of inelastic scattering length. We also do not believe that magnetic impurities are responsible for that, since all types of films were grown in the same chamber with the same in the same environment. So there is no reason that magnetic doping can choose particular films to enter. Further confirmation of the theoretical considerations we get by measuring weak antilocalization as a function of a parallel magnetic field. So calculations shown that symmetry, mirror symmetry breaking is translated to some additional magnetic field contribution. So it means that in mirror symmetry broken case, weak antilocalization is destroyed faster than compared to the case where mirror symmetry is obeyed. And indeed, we saw it in experiment. If we compare the results of magnetoconductivity for the films with the similar compositions, we see that systematically in the films with selenium cover, weak antilocalization is destroyed in lower fields compared to the uncovered cases. We also try to fit the weak antilocalization in the parallel magnetic field with the conventional expression for parallel field effect. And we saw that both fitting coefficients, alpha and beta, have some discrepancies from the expected values. So, and that's we think is kind of a confirmation that this effect is not covered by conventional theories, but depends on the symmetry. Right. So these results are somehow aligned with the several results on the spin result ARPES measurements. So the quantized Berry phase usually means that there is a certain texture in the orbital or spin momentum in the reciprocal space. So it means that such texture is present in both topological and non-topological films. And if one look into the literature, one can find that there were several works on spin-resolved ARPES measurements in both topological insulators and topological crystalline insulators, where people try to move through the topological transition and see whether the spin polarization occurs only in topological case, but no, it was present in both cases, in topological and trivial. So it was checked for lectin selenide 001 surfaces, by the way, on the samples produced by in the group of Professor Story. So we tried to see whether this is the case for 111 surface in lectin selenides. And we saw that the spin polarization is present in both topological and trivial phases, and the value of the spin polarization is quite similar in this case. So in this case, there is also not that much difference between topological and trivial cases. And in that sense, it is quite aligned with the results we obtained for weak antilocalization. So this is the summary of published work. So we discussed how different symmetries are affecting Berry phase quantizations, and particularly that crystal symmetry can be responsible for the Berry phase quantization. So from theory considerations, we conclude that weak antilocalization is not influenced by the band ordering, so it exists in both inverted and trivial regimes. We also calculated that weak antilocalization should be sensitive to the presence of crystal symmetries. And both of these predictions we confirmed by experiment, by measuring magnetoconductivity. And this results are in qualitative agreement with the spin result ARPS measurements, which we done recently, and both results are summarized in these two papers. So now I will talk about some results within two directions we are doing right now, which are unpublished. And the first one is I will tell about our work on quantum wells. Also, it is topological crystalline insulator quantum wells, where we expect to see quantum transport, such as quantum Hall effect, and hopefully to see the evidence for topological edge transport when we move to the gap. So in topological insulators, this topological edge transport is manifest itself as a quantum spin Hall effect, which was measured quite a long time ago in mercury telluride quantum wells. And it was shown that in TCI, in topological crystalline insulators, this topological edge transport has some oscillatory character depending on the thickness of the films. So it was calculated independently in MIT by Liang Fu, and also here in FPAN in Professor Buchka group. So both of them saw that band inversion oscillate with the thickness. So that's one hallmark of this effect, but also it should also oscillate with the strength of the electric potential. So in principle, quantum wells from 4/6 semiconductors were studied in the literature. So, but usually it was used, lead telluride was used as a material for the quantum wells. And the typical structure looked like this. So on barium fluoride, people grew pretty thick lead European telluride buffer, lead telluride quantum well. Bismuth was used as a dopant. And then it was followed by lead European telluride cap layer. So the band structure of such quantum well is quite anisotropic. So it has 4 pockets in L points. So they have a shape of the ellipsoid. One ellipsoid is parallel to 111 orientation. It is called longitudinal valley in such quantum wells, and 3 others are rotated by 71 degrees to the normal to the surface, and they are called oblique valleys. So these ellipsoids are quite anisotropic in the case of tellurides with a pretty high anisotropy parameter. Sorry. But in case of selenides, the anisotropy is not that large. So this 4/6 quantum wells has band type 1 band alignment with negligible offsets, and that's how the energy gaps depend on the temperature in such a quantum well. So such material were studied also here in FPAN by Professor Grabetsky, who saw quantization of the conductance in narrow channels. He also looked for the signatures of the topological edge transport, and he confirmed that in lead telluride it is absent. In Brazil, people tried to see quantum Hall effect in lead telluride. So they saw it in both N-type and P-type samples, but no one was looking for quantum wells with the topological compositions. So this is the several quantum wells which we grew. So it is based on lead-tin selenide with the tin content corresponding to the topological composition. Bismuth was used as a N-type dopant, and this is the simple structure which was grown by the MBE. We etched such whole bars to check magnetotransport. It has two arms at 90 degrees to each other to see whether an isotropic band structure affects the magnetotransport. So this is typical results we are getting on such quantum wells. So here I'm showing the Schoenfeld-Degas oscillations of resistance versus magnetic field for 50 and 10 nanometers. So one can easily see here that in 50 nanometer there is clearly more than one frequency of the oscillations, and the oscillations are starting in pretty low magnetic fields of 0.5 Tesla. However, in 10 nanometers, one barely can see other frequencies, only one frequency, and oscillation starts around 3 Tesla. So it means that mobility is considerably reduced in thinner quantum wells, which is quite expected, because the europium, which was used as a element for the barriers, cuts the mobility quite considerably in these compounds. So by doing yes?
These different curves are for different temperatures, I believe, yes?
Yes. This is temperature dependence. So blue color is for low temperatures, around starting from 0.3 Kelvin up to around 20 Kelvin for the red curves. We performed Fourier analysis of these oscillations as a function of 1 over b, and we confirmed that indeed for 50 nanometer case we see two well distinguished frequencies. However, for 10 nanometer we do not see two different frequencies. We see quite wide peak, which is doubling at the very low temperature. So whether it's an artifact or it is real, it's still a question. So from temperature dependence, we can estimate the effective mass, which is approximately 0.14, 0.15 of the electron mass, and that's the value which one can calculate from a simple KP model for lead tin selenide with this particular tin composition. What is important also here that within these fields we do not see any difference between two different crystal orientations. So at least up to 7 Tesla, the system is quite isotropic. So to check whether the oscillations are 3D or they have 2D character, we measured them as a function of tilt angle. So the sample was rotated in the field, and we look how the oscillations pattern is changing with the tilt angle. So one can clearly see that oscillation pattern is changing with the tilt field. So we also plot it as a function of 1 over b perpendicular. And in two-dimensional case, the oscillation pattern should not change in 1 over b perpendicular. And indeed, for 10 nanometer, we see that oscillation pattern is the same. However, in 50 nanometer, the situation is more complex. And by doing FFT for each field scan, we see that in principle, it is 2D. So the peaks are staying at the same, more or less at the same peak, but they still somehow evolve. And in 10 nanometer case, the picture is not changing much, but in both cases, the oscillations are strongly damped at the angles close to the parallel magnetic field. Another important question is what is the phase of the oscillations? Because it is believed that in the Dirac systems, the phase of Shoemaker gas oscillations can be a source of information about the Berry phase. So by fitting the results for 50 nanometer quantum well with the sum of two cosine, we achieved a pretty nice fit. The black dots are experimental values, and the red curve is a result of the fit. So the oscillation pattern is sketched up pretty nicely. And for both cosines we used for the fitting, we get the phases close to 0.5, which indicates that this is consistent with the directness of the material. However, for other thicknesses, such approach using single cosine result in quite random values. So we also checked it with this approach of plotting Landau level index by assigning integer values to the minima and half integer to the maxima, and plotting and fitting it with the linear curve as a function of 1 over b. So we achieved also quite randomized values. So that's we do not sure why it's happening. So one idea is that if it is indeed two frequencies present, one is two close frequencies and one is trivial with a zero Berry phase, and another is Dirac with a pi Berry phase, then in experiment it should look like one single cosine. This blue one curve is the sum of two cosines shifted by pi with two different frequencies, and the orange is a single cosine fit. And one can get the phase shift of this single cosine fit better as more or less any value depending on the ratio of the amplitudes of the input to cosines. So the doubling of the FFT peak for 10 nanometer indeed can be a signature of two frequencies with different Berry phase, but that is still the work in progress to check it. So, but the final goal is to see the signatures of the quantum Hall effect and potentially to go to the gap and to achieve to see any signatures of the topological edge transport. So the for quantum Hall effect, one thing can be usage of high magnetic fields, because in lab tellurides people saw quantum Hall effect in pretty high fields, more than 10 Tesla. Another approach is to bring Fermi level down, which can be achieved by bismuth doping, and it was shown that in similar compounds, the bismuth can be quite effective dopant by moving the system from p-type conduction to n-type conduction. And finally, one can employ electrostatic gating. This is the results I got from one of the quantum wells. So one can finally, after achieving pretty low carrier density by doping, can further move it with electrostatic gating. And in the group of Professor Buchka, it was shown that leptin selenide in principle can be a host for topological edge transport, and it also should have some thickness dependent. So, and these two directions are the future work with this project. So far I've shown that the high quality quantum wells we did by MB growth, and in these quantum wells we saw very pronounced Shubnikov-Degas oscillations. So and indeed for 50 nanometer it is clearly two-dimensional system still, so we do not see any transition for 3D so far. And we saw some signatures of non-trivial Berry phase in the quantum wells, though only 50 nanometer was clearly showing that it is pi Berry phase. And the last thing I wanted to talk about is alpha tin or gray tin. This is another direction we are working right now. So the tin as a solid has two modifications. So one is high temperature, the metallic one with the white color. That's why it's usually called as a white tin or beta tin. This is high temperature phase. And low temperature phase is alpha tin, which is a little bit grayish color. That's why it's called sometimes as a gray tin. And the transformation occurs a little bit lower than room temperature, around 13 Celsius. So the alpha tin has a diamond crystal structure with the lattice constant of 6.49, and it is believed to be a semi-metal, so it is a gapless semiconductor with a zero band gap. And as a thin film, it is usually grown on indium antimonite or cadmium telluride. Both has zinc blende structure, and lattice constant slightly lower than the alpha tin. So, but lattice constant is pretty high. So the difference in the lattice, so the fact that the lattice constants are similar, so the substrate stabilize this gray tin form of tin on one hand, but on the other hand it induces some in-plane strains which are resulting in the opposite sign of strains into in the z direction. So, and it was shown that depending on the sign of the strains in z directions, the zero gap semiconductor can go either to topological insulator or to Dirac semi-metal phase. So what is important here that usually much or more often indium antimonide is used as a substrate for that, but it has quite a high doping. It is also narrow band, narrow gap semiconductor. So in transport experiments, it usually make some parallel conductance. So for transport measurements, it is relatively not very convenient substrate. On the other hand, cadmium telluride is less often used, but it is wide band gap semiconductor, and it is insulating. So for transport measurements, cadmium telluride is better. And we use the cadmium telluride buffer as a substrate to grow alpha tin in this project. So, but first let's take a look how the band structure of gray tin looks like. This is accepted Groove's pole model for the gray tin, which has a conduction band touching the heavy hole band at gamma point. The light hole band is laying further down. We also have a small pocket at L point, which is laying a little bit higher than the edge of the conduction band. So we will concentrate on this part where the conduction band is touching the valence band. It has such shape, so it's zero gap semiconductor with the parabolic dispersion or Latinger semi-metal. So let's see how the band structure is affected by external perturbations, such as in-plane strain. So in-plane strain we take as was above as compressive. So it results in the tensile out-of-plane strains. And we see that these two bands overlap and the gap opens. But in these 2 points, we have almost linear, we have a near linear dispersion. So it means that the material is transformed to the Dirac semi-metal phase. And further, if we consider in-plane magnetic field, we see that these 2 Dirac points are split further into 2 so-called Weil semi-metal points. So it should be Dirac semi-metal in zero magnetic field and Weil semi-metal in the presence of parallel magnetic field. So we used MBE to grow alpha-tin on cadmium telluride buffer layers. So here in F1, the read pattern shown high quality of the layers. With the TM analysis, we saw very sharp edge between the cadmium telluride and alpha-tin. The films were checked with XRD, which showed high crystalline quality of the films, absence of any other phases, such as high temperature precipitates of tin or beta tin. So XRD also confirmed that the layers are fully strained. So it means that we should see Dirac semi-metal behavior, and IFM showed very low roughness of the film, which is also confirmation of high quality of the grown films. So these films were checked with ARPES, which okay, 5 minutes. So the ARPES shown very nice Dirac cones with the presence of several types of surface states. We also checked core level spectroscopy, which showed that only the tin is present, so it is do not have any other dopants. For magnetotransport, we etched such L-shape, again, hole bars to see the effect of parallel field when it is aligned with the current and when it's perpendicular to the current. So we used 4 different thicknesses, 50, 100, 150, 200 nanometers. Okay, we saw that the resistance versus temperature depends as it should depend for the semi-metal or semiconductor, not as for metal. So the resistance grows with the cooling down, and that is usually explained as depopulation of this L-point pocket, which is laying higher than the edge of the conduction band. And at low temperature, we saw that resistance do not change very much with the temperature, but the trend depends on the thickness of the film. So the magnetotransport in the low temperature regime, which we focused mostly to not to complicate the analysis with the consideration of the L band. So at low temperature, we saw presence of 2 types of carriers, both N and P type. So if we plot the sheet density of holes and electrons versus thickness, we will see that the electron sheet density depends linearly on the thickness. From this, we can conclude that the electrons are coming from the bulk states. And p-type, the holes do not show any dependence on the thickness, which indicates that they are coming mostly from some interfaces or something else. So we are not 100% sure at the moment where the holes are coming here. So we checked how the magnetic resistance looks in the presence of in-plane magnetic field. We call the whole bar where the magnetic field is parallel to the current as HB1, whole bar 1, and where it's perpendicular to the current as HB2, whole bar 2. And we see that magnetic resistance in both cases have different signs. In HB1, where the current is parallel to the magnetic field, we have negative magnetic resistance. In another whole bar, we have positive magnetic resistance. And that's the behavior which was expected for the while semi-metal phase. It is called the chiral anomaly, and it should have a parabolic dependence on the magnetic field as was calculated. However, in experiment, it was in other materials, it was rarely found the parabolic behavior, and usually people explain it as that it is caused by the presence of other effects. So the chiral anomaly effect is expected for while semi-metals. So because in-plane magnetic field induces some additional current, so-called axial current, which depends on both magnetic field So, and this additional axial current manifests itself as a positive contribution to the conductivity. So there are other effects which can lead to the negative magnetic resistance. So the most common we considered as current jetting, weak localization, or quantum limit. The last one is clearly not the case. The quantum limit we did not reach at any field, because we can see that quantum oscillations persist in all range of the fields, which means that we do not achieve the lowest Landau level. The current jetting we also do not believe is the case. In HB1 we have two types of contacts. One is laying on the edge of the whole bar, another is covering the whole channel. So it means and these two contacts show the same behavior. We by comparing results from this two set of contacts, we exclude current jetting. And finally, weak localization for 3D system, it should depend on square root of magnetic field. And we do not see the square root behavior in the full range of magnetic field. So we also do not believe that this is the case. And it is also kind of anisotropic in this case, because in HB2 we have positive magnetic resistance. Finally, we made some analysis of quantum oscillation in this system. We saw very nice oscillations. We compared perpendicular and parallel field. We see that the frequencies in these two cases are slightly different, which is can be explained by considering the cross section of the band structure in the conduction band. So the cross section in one case is larger than in another one, and that reflects manifests itself as a different frequency. We also calculated the phase difference. So this 1/8 offset of the phase is also determined by the cross-section extremum, whether it's minimum or maximum. That's where this sign comes from, and it is also consistent with the band structure calculations. And the only thing we do not quite well understand that the Berry phase, this 0.5 phase shift, depend on the thickness, which changing from no phase shift to pi phase shift for 200 nanometers. That's something we do not understand at the moment, so we're still thinking about it. And this is a short summary of the results that we considered the band structure. We looked how it is changing as a function of external perturbations. We grew high quality alpha-tin layers on cadmium telluride substrate, so the magnetic resistance measurements are not abstracted by the parallel conductance from the substrate. We checked magnetic resistance in both in different field orientations, and we did Schönfeld gas analysis to extract the phase shift. This is acknowledgement slides where I want to thank all my collaborators. So the theory of symmetry protection of Berry phase was done by Wojtek Brzezinski and Timo Hart. So XRD was assisted by Dr. Domagala. IFM was done by Marta Areshkevich. And TM measurements were performed by Piotr Duzhevsky and Kurovska. Andrei Tsacha and Andrei Verkhalov assisted in ARPES measurements. Günter Spritz also assisted with quantum well growth. Rafał Rudniewski helped with the spin result ARPES and also with growing the buffers for alpha-tin. Tomek Wojciechowski assisted with EDX analysis, and he also is responsible for the smooth running of all equipment for processing which we used. Kuba Palachinsky did almost all work on alpha-tin magnetotransport and processing, and Bartosz Turovsky did most of the ARPES measurements and also assisted with the growth. I also want to thank Zbyszek Adamos and Wojtek Zaleszczyk, both assisted in transport and growth procedures, and the whole work would not be possible without Valentin Balabuyev, who did all the growth, did all ARPES measurements, and also performed XRD analysis of all samples here. And I also thank Tomasz Little, Tomasz Wojtowicz, both responsible for their part of the work and also for overall scientific management of our unit. Okay, thanks. That's all.